Building a ship takes years of meticulous engineering, but getting it into the ocean has historically required a controlled disaster. For decades, the traditional launch was a 60-second window of extreme physical trauma. The moment the retaining triggers release, thousands of tons of steel are surrendered completely to gravity. Before the vessel ever touches the water, its entire weight sits balanced on a highly stressed foundation. Down here, the hold rests on an inclined, heavily lubricated timber and steel cradle. Once the sliding ways begin to move, the ship accelerates down the concrete ramp. A massive hull can hit speeds over 10 kilometers an hour as it careens backward toward the harbor. In this environment, momentum is the only thing that matters. Managing a massive structure in freefall is inherently volatile, pushing naval architects to seek a more predictable approach. The absolute peak of that danger occurs halfway through the descent, during what engineers call the tipping moment. As the stern enters the harbor, the water's buoyancy begins to act on the immersed steel. This diagram illustrates the opposing forces. Gravity pulls down at the center of mass, while buoyancy pushes up at the rear. This upward lift forces the hull's weight to pivot onto temporary supports near the bow, called forward poppets. The math must be perfect. If buoyancy exceeds weight too early, the bow rises before the ship fully floats, causing the poppets to overload and fail. When those supports collapse, the steel hull drops violently onto the concrete slipway. A minor miscalculation in the launch geometry can severely damage the vessel before it ever leaves the yard. Even if the ship safely reaches the water, it is still moving fast enough to hit the opposite bank of the harbor. To stop it, shipyards tied hundreds of tons of anchor chain to the sides, forcing the heavy links to drag across the harbor floor to progressively bleed off that momentum. Throwing a ship down a ramp is essentially an exercise in surviving dynamic stress. To build larger, more complex vessels, the industry had to find a way to remove gravity from the equation entirely. The solution to the violence of a traditional launch was surprisingly elegant. Instead of sliding the ship down a slope to meet the ocean, modern shipbuilders bring the water up to the ship. This dry building dock is a floodable basin carved into the earth. Crews assemble the hull on a perfectly level concrete floor. Without an inclined ramp or sliding cradle, the vessel sits completely secure on rows of heavy keel blocks for the entire build. When the hull is structurally complete and thoroughly tested, the heavy dock gates are sealed. Engineers open massive valves, allowing the sea to slowly fill the basin. In a moment of wonder, the chaotic 60-second free fall of the slipway is replaced by the slow, deliberate predictability of rising water. Naval architects determine precisely when the ship will lift long before the water valves are opened. They calculate a specific water line called the float-off draft. As water rises, the upward force of hydrostatic pressure continuously increases. The ship remains pinned until the buoyant force perfectly counteracts the downward weight of the steel. Workers monitor the painted draft marks, watching the waterline climb toward that calculated threshold. But visual checks are just the first layer of confirmation. In modern docks, electronic load cells are installed beneath the keel blocks to measure the exact tonnage pressing down on the concrete. As the water pushes up, pressure on those sensors steadily drops. When every single load cell reads exactly 0, the ship is gently, silently waterborne. There is no crashing spray, no tipping moment, and no runaway kinetic energy. Achieving lift through pure hydrostatic equilibrium removes the immense physical risk from a ship's berth. Resting quietly inside the flooded dock, the hull is entirely stress-free. It can now be moved by tugboats without ever having launched in the traditional sense. This shift in methodology was born out of absolute necessity. As global supply chains expanded, the market demanded cargo capacities that eventually outgrew the slipway. Today's colossal crude carriers and container ships weigh tens of thousands of tons before they even load their cargo. Dropping structures of this magnitude down an inclined ramp would tear the hulls apart under their own immense weight. To accommodate these leviathans, major shipyards operate vast networks of building docks. They assemble multiple superstructures side by side, achieving massive production volumes without ever rolling a single hull into the harbor. By prioritizing the slow certainty of rising water over the brute force of gravity, engineers bypassed the structural loads that once limited ship size. Trading dynamic chaos for calculation is what made the current generation of megaships physically viable.